In this brief video, I want to talk about the actual amount of energy stored in a capacitor. So we've been talking about capacitors as devices that store electric potential energy, but we haven't actually talked about how much potential energy gets stored in a capacitor. So that's the question: what is the potential energy stored in a capacitor? And there are formal ways to derive this, but I just sort of want to make an argument based on units here to try to explain what the potential energy is. And what I want to think about is I want to think about the fact that we already know that potential energy, U, is connected to electric potential by an amount of charge. What we said is that potential energy is electric potential multiplied by charge, or the way we defined electric potential, right, was potential energy divided by an amount of charge. So we know that electric potential is related to potential energy. And so for a capacitor, then what we could think about is, well, if we knew how much charge was on the capacitor, Q, and we knew the potential on that capacitor, V, then we could calculate U, right? Now, there's a little bit of a trickiness here, though, in that capacitors have two plates, right? And they have a potential difference, V across those two plates, and plus Q up here, and minus Q down here. And the thing that is a little bit tricky here is that potential ultimately is related to how much work you need to do to go sort of from downhill to uphill, right? How much work does that take? So when we think about the potential that this is at, well, you have a bunch of Q up here that's at high potential and a bunch of Q here that's at zero potential. So in fact, when we write down this formula, you actually need sort of the average potential, right? If down here you're at zero and up here you're at V, what ends up mattering for the potential in a capacitor is sort of the average value, which would be half of V. And so the formal formula for U in a capacitor is actually U equals U in a capacitor is 1/2 times Q times V, because it ends up just being the average potential kind of in the middle of the capacitor is relevant for thinking about the total potential stored on that capacitor. Now, there are a couple other ways of writing this formula, because you also remember that we said that capacitance is defined to be Q over V, right? So we can rewrite that a couple different ways. We can say that Q is C times V. And if we do that, we could take this formula and plug it in over here for Q, right? And we get that U of a capacitor then is going to be 1/2 times C times V. So that's C V squared. That's just from taking and plugging this formula into there, right? Or if I rearrange this one other way, I could write this instead as V equals Q over C. And if I do that, well, now let's plug in Q over C here for the V. And what we'll get is you'll get a Q squared over C squared, but then one of the C's will cancel. And the other way we can write this capacitance energy in a capacitor formula then is going to be 1/2 times Q squared divided by C. So here you have it, sort of three different ways of writing the amount of energy in a capacitor.